Well, today I'm going to talk about the novel narrowband high gamma power modulation observed during complex rhythmic motor skill execution. And I need to start with this disclaimer that, when I wrote that abstract, I thought, this narrow high frequency band activity is going to be something novel and interesting, but we found even more interesting things. So today I'm going to actually talk about it. And the complex motor skill I mean is juggling, 3-ball jugglings. Well, why juggling? There are a couple of reasons for that. One is that the classical motor skill learning studies is about using this simple ballistic and that which has a clear onset and offset, this kind of simple motor executions. But juggling is, in contrast, complex and very demanding. You have to concentrate, otherwise you will lose, drop the ball. And also, juggling has relatively fast cycle, so it's easy to gain like thousands of the trials, which is good to compensate for the relatively poor signal-to-noise ratio of the scalp-recorded EEG during the performance of the juggling. A lot of artifact is expected, of course. And in Tokyo Tech in Japan, there is an ongoing study of the extension of this juggling using the very novel visual haptic virtual reality system, in which subjects use this goggle and a haptic virtual reality device so that we can control the gravity and the speed of the ball, and we observe how it affects the learning. Our hypothesis is of course, if the ball falls slower, then it's easier to learn the juggling. So that's actually presented in the poster P12 by Hyun-Suk Kim. Okay, so this is the experimental setup. And today I was ready to give you the juggling performance here, but unfortunately my suitcase was lost in the New York airport. So it's regrettable that I can't do that demonstration here, but I'm a subject 6 of this project, so I can do the juggle. So basically the strategy is we used these luminous balls so that we can separate it using the image processing from the background, so that we can trace the balls and hands. And while subject performs the juggling, we record the high density, like 205 channel EEG. So the first result is the behavioral measures. So there are 2 hands and 3 balls. So we analyzed the relations across the 3 objects. So in the top plot, you see, all plots, you have 5 lines. So 2 lines are for the hands, 3 lines are for the balls. There is actually a paper by Claude Shannon about the juggling, and he talks about the relation between those hands and balls, but this is a demonstration of how his theory can be seen in empirical data. And performance metric number 1 is how long the subject can continue the juggling. And if someone is very skilled, then they never drop the ball, right? But if the subject is not that experienced, then they drop the ball very often. So that's the difference. And we collected like 13 subjects data, and we found 3 of them have outstanding performance. They can juggle in average more than like 300-400 cycles like this. On the other hand, the average performers, they can continue only up to like 50-60 cycles. So there is a very clear performance difference. So that's going to be one empirical criteria to separate the groups data. And this is how we quantified the juggling performance. So high performers, which is the left panel, you see the tight trajectories of the hand and balls, and the apex of the balls are marked, and also the catching point and throwing point of the hand are also marked. And average performers, you can see clearly the larger standard deviation on the lateral axis. So that's also the behavioral metric of the performance level. And as expected, we observed those 3 high performers, and their standard deviation is really tight compared with an average performance, as you can see in the figure B. Okay, here is the EEG result number 1. This is the result from using the independent component analysis, and we found those the independent component from all the subjects that is centered in inferior parietal regions. And what's interesting about these EEG sources is that in a single trial analysis, there is a jitter of this ball apex position. So sometimes the ball apex goes to right or to left. Then interestingly, we found that the EEG power in this region shows increase or decrease depending on if it goes left or right. So what it means is that actually this ball apex position is encoded by the inferior parietal EEG power. So that was the main finding here. The next analysis is to separate the average performers and high performers and what EEG difference we can see. So this is one example of left frontal electrode, and the result I'm going to show you hereafter is after applying the spline Laplacian method. So spline Laplacian is the algorithm used in edge detection. So it's gonna remove the effect of the volume conduction. So what you see here in the data is actually theoretically the equivalent of the Dura potential image, which does not have the influence of the volume conduction. So now the sensors, the electrode, are maximally sensitive to the cortical activities right underneath the electrode metal surface. Now the average performers, they do show some structures in the time frequency domain, but in the high performers, wow, there is blue, red, blue, red, blue, red pattern in the multiple layers across the frequencies. So this alone can give you the very clear sense that high performance EEG pattern is much more well structured in the time frequency wise, right? And we continue to see this one sample electrode in the left frontal. And again, this is not the scalp recording per se, but after applying the spline Laplacian, so no volume conduction. And there are 2 frequency bands I picked up. One is about 2.9 hertz, and the other one is a 4.5 hertz. Those 2 frequencies, the EEG power oscillate in a different phase. And this phenomena was only found in the high performers. So this is one evidence of how this the performance difference is represented in the EEG, and we investigate this further. So so there is a phase difference between the 2.9 hertz and 4.5 hertz, and they oscillate like this. So one chases after. So you can see this. Okay. Okay, so no movie available, unfortunately. But I'm going to show you the next slide. Oh, excuse me. Okay, yeah, forget about it. So, so this cross-frequency phase shifting is observed in this way. And this is, I thought it would be interesting to see the whole brain phase map. So this phase shift seems to have the gradation across the whole the surface of the cortex, theoretically speaking. After applying the spline Laplacian, we can discuss that. And this is a visualization of the all high performance average, how this 2 low frequency power oscillation relates from frontal to occipital. Apparently, there is a gradual phase shift from frontal to central, from 169 degrees, which is almost the anti-phase, and now that phase difference becomes smaller and smaller as you approach to the central to the parietal region. The final piece of the evidence of this study is the longitudinal changes that reflect the training effects. So this is from the ongoing data collection happening in Tokyo Tech. And here what we did was to apply this the functional connectivity analysis across the EEG channels. And this method called the debiased weighted phase locking index, this method can eliminate the effect of the volume conduction. So it's not like a spline Laplacian, but effectively we can talk about what's happening in, again, the like a Dura surface level of the potential map. And from day 1 to day 10, we can see this the within frontal connection between the one channel that is shown in the star mark and other regions. If the connectivity is high, then it's going to be red. But that red within the frontal region is reduced from day 1, day 5 to day 10. So the reduction of the this functional connectivity within frontal cortex is probably the evidence of learning. So my conclusion is that inferior parietal EEG sources encode apex positions, and skilled jugglers shows their EEG is more organized in a spatio-temporal way, and juggling learning may be associated with the reduction of the connectivity within the frontal regions. So that's all. Thank you very much.
Any questions? Yeah.
So, thank you. I'm here. So why do you think apex? Why do you think apex?
Sorry. Wait, sorry.
So you think apex is the most accurate, or do you think other parts of the trajectory are encoded elsewhere in the brain?
There are some evidence that apex is probably the most important metric in juggling, so that's why we used apex.
Hi, thanks. So I just wonder, what about the higher frequency? And do you look at any coupling with the gamma? Because you looked at the theta alpha range for the effects you showed.
The high frequency is difficult to find, and only the ICA result showed it. But the ICA result does not have uniformity of the sensitivity. In other words, if ICA finds those components containing the high frequency activities, then we can report it. But the issue is there is no guarantee that ICA returns the same result across all the subjects. So that imbalanced or variability of the ICA sensitivity to that high frequency was one of the practical problems in performing this analysis.
Thanks. More questions? Okay, thanks again the speaker.